Morning, everyone. You guys can unmute yourself for right now. We can have a brief talk before we start. And you can also turn your camera on so we can see each other. It's been a while.
Hello.
Hi. How you guys doing?
Good.
Good.
That's good. That's good. All right.
What?
Hi.
Hi.
I can see some of you guys are still in bed, huh? That's good. All right. So we'll get started. So I want to talk to you about the exam 2 you guys have been doing. You guys done pretty good on exam 2. You all got the grade exam back, right? Anyone didn't?
No, I got mine.
Okay, that's good. All right. So if you didn't, let me know. I think I sent every one of you of yours. So you guys had average of 77% this time, which is very good compared to last time. You guys having like 74%. So for right now, the average of the class is at very good standing. You guys on average are having a B plus in the class. So some of you guys have A's and A minus. Some of you guys have B's and then C's. Okay, so that's what we have so far in the class. So keep it up. I think you guys are doing pretty good. Okay. So during the lecture, so whenever you guys want have question, you want to talk, you can just unmute yourself. Okay. I know a lot of you guys would just mute yourself for right now because if everyone is unmute, then there might be crazy background noise going on in the back. But whenever you guys feel like to talk, you can unmute yourself. Okay. So exam 2, so I actually there was only 2 versions of exam 2. So you get either you receive version A or version B. Okay, so we can take a quick look on the solutions. Let me share my screen to you guys over here. So on the Moodle side of this class, I uploaded the version A and version B of the solutions. Okay, so we can take a look at these 2 versions. Let me see. So this is the solution to version A. So if you get the exam file number at the end labeled as 1471013, then you have this version A. Okay. Now I don't have the problems over here written here, but you can refer to yours. So this one, the first one on version A is about electric field. You have electric field provided by 2 charges, Q1 and Q2 at this one. So then for positive charge, the electric field at this point will be pointing away from the positive charge. So this guy is pointing to the right. Okay, E1 is pointing to the right, and then E2 would be coming from the negative charge over here, will be pointing to the left. So the overall will be E1 plus E2 in vector form. But this is one-dimensional problem here. So then we'll just take positive or negative signs for the direction. So for E1 will be pointing towards the positive side. So then it's positive. For E2 it will be negative because it's pointing towards to the left. Okay, the negative side. So then you'll plug in the numbers. At the end, you'll get minus 179 newtons per coulomb. You'll just take the magnitude. We are just looking for the magnitude on this one. And the second one here is very similar to the one of the homework problems. So you have 2 charged particles. They are hung by this string to the ceiling over here, they make an angle of theta, which is given as 28 degrees. I changed the number a little bit, but pretty much and then the length I changed it to 1.2 meters, but other than that, it's the same problem. So then you'll use the electric force. Okay, it's going to be from the free body diagram here. If you look at the geometry over here, it's going to be mg tangent theta. And then it's also going to be equal to k q1, q2, which q1, q2 are both equal to q. So q square over r square, r will be the distance between these two balls. Okay, and this is from Coulomb's law. So you get electric force both from the free body diagram and then also from the Coulomb's law. Then you can set the two expressions equal to each other. You can solve for the Q. Okay, we'll be doing it that way. The third one, it's combination of capacitors in series and in parallel. You can refer to the figure. So then you'll be using the rules when the capacitors are in parallel and then in series. Okay, treat the ones purely in parallel together here, 1 and 2, and then this the third branch over here, you can do the same thing. Okay, so at the end, it's going to be 11.4 microfarad. The fourth one here, you guys also for version B, you also got this problem. It's the same here, but I think it's a different number, problem number. Like I think it's problem number 5 in the version B. But this one, a lot of you guys didn't get this one right. For this one, you need to use Gauss's law, where it says the flux of the electric flux would be equal to the charge enclosed divided by epsilon naught. Okay, so this is the flux equal to electric field times the surface or spherical area 4 pi r squared. Okay, so then from there you can calculate what will be the E field. Okay, so E field now Q enclosed in here because you are a distance that is something 0.2, where the radius of the sphere is 0.25. So you are within this sphere. So you don't take the whole charge of the sphere. You will just have the part of the charge of the sphere. Okay, so take this small sphere over here, then calculate what's the charge inside, including this small sphere. So that's the Q here. Then take this expression Q for the expression over here. You'll calculate your E field. Okay, so that's the only trick. Most of you guys didn't catch that one. So it's going to be only part of the overall charge. Okay. The fifth one here on version A, I think. Well, fifth one and sixth one. So in version A, I split them into two problems. In version B, you have combined them together as problem 7, I think. But pretty much the same thing here. So you have two charges here, and then there's a third charge over here. So on problem 5 here, you're looking for the overall potential at this point. So potential is given by, for each charged particle is given by kq over r. So you have two of them, you just add them together. Okay. You want to look at the geometry over here to get R1 and R2. They are equal to each other. Okay. And then you plug in the numbers. That gives you the potential at this point over here, where the third charge is closer to 0 at its y location. Okay. Now on the sixth problem here, you're looking for the speed when it is this charge, the third charge is released. Then you will move towards away from the two charges on the y-axis. So it's going to be somewhere here later at some point. Now the first thing you want to do is figure out what's the potential at this point. Okay, so again, you're doing potential equal to kq1, q2, but you use V2. It turns out potential right here is smaller than this guy over here. Okay, so once you have that, then you can apply conservation of energy over here, which says kinetic energy, okay, 1/2 mv squared plus the potential energy, electric potential energy, Q3V1 is equal to 1/2 m V2 squared, small v stands for velocity, large V stands for potential, okay, plus Q3V2. Q3 V2. So then from there you can solve for your velocity V2. So this guy is being at rest initially, so that's 0. Okay, so it's about 3.2 at the end. Okay. Number 7 in version A, it's about calculating the capacitance of capacitor when there's a dielectric inside it. You guys also got the this one in the version B. Okay, so it's similar. So you use this equation when there's dielectric. So you have kappa here, looks like a K, but it's kappa epsilon 0 A divided by D. All right, you just plug in the numbers. Okay, so this one is easier. Number 8 here, I think we went through this in class. You also got this one in one of your homework problems. So there's a short circuit in a very short time period. Is asking what's the temperature raise of the material involved. So the energy, electric energy is given by potential power times T. And then the energy that received by the material is also equal to the energy. Okay, so then that causes the temperature raise according to specific heat definition. Q equals to mc delta T. You're looking for delta T here. So you set P times T equals to mc delta T over here. Then you solve for delta T. Okay. Number 9 in version A, you also got number 9 in version B. Okay, so it's the same. But we are asking for different current. I think in A, we are looking for current going through this resistor. In version B, we are looking for current going through this resistor. Okay, so but you'll be using Kirchhoff's rules here. You apply junction rule 1 time and then apply loop rules 2 times. Okay, so at the end, you'll have 3 equations with 3 unknowns. You can solve for the I1, I2, I3 as the unknowns. Okay, the currents as unknowns. Depending on what you are looking for, you'll take different answers at the end. Okay. Number 10, you also got this one in version B, but you in version B it has a different slide number. Okay, slightly different number. So when you are charging a capacitor, the current is equal to, this is the equation you want to use. Okay, make sure you pick the right equation here. Then for the rest, you just plug in the numbers. Okay. You guys might have difficult plugging numbers in your calculator, but you can confirm it again this time. Okay, looking at the solution. So plugging the numbers, it's going to be 2.76. Okay, so this is version A. All right, now let's also have a quick look on version B. Let me just share the screen of my version B. I think it's this one right here. Okay, over here. All right, so version B, the first one, it's actually about electric force. Okay, but because electric force is equal to the charge times the electric field is experienced, so then it's also about the electric field. Okay, so this one, then at the end we are also looking at the electric field. So you are given 2 charges at 2 locations, and then you are looking for at the 3rd location where the electric field will be 0. So that means E1 and E2 will be equal to each other. So you set it up that way, then you are going to say this unknown location as X, then you will be solving for X. Okay, so the K and K here, KQ1 over R1 square will be E1, KQ2 over R2 square will be E2. The K and K is the same coefficients, they will cancel out. Okay, so it will be 5.0 over X square will be R1, and 2.5 over X minus 2.25 square, okay, it will be R2. So then you'll be solving for X. Okay, so at the end it's going to be this number. Problem 2 and 3, you guys have this in one of your homework assignments problems. So you are given 2 charges totaling 7.5 microcoulomb, and then the force between them is 0.055 newtons. Okay, so then you can set up 2 equations. You can have this one Q1 plus Q2 equal to 7.5 microcoulombs. Then you can apply Coulomb's law. So K Q1 Q2 over separation square is equal to 0.55. Okay, so you have two equations. You solve for the two unknowns Q1 and Q2. Okay, so at the end you'll have a quadratic equation. You can solve for Q1 and Q2. Q1 and Q2 will be the answers for problem 2 and 3. Okay. Number 4 here about deflection of a charged particle through an electric field. So in this case, in the y direction, the charged particle will experience acceleration due to electric force. In the x direction, it will just go, the velocity will not change in that direction. Okay, so because there's no force in x direction. So then x direction, the velocity will be the initial velocity v0. You will be looking for the y direction velocity at the end when it exits this region. So you'll be having t first, okay, calculating t first will be equal to the x, the distance, horizontal distance, divided by the horizontal velocity, okay? The initial velocity that gives you the time it takes to go through this region. Then acceleration in this region will be equal to the electric force divided by the mass of the charged particle, which is an electron. Okay, so they plug in the numbers, you'll get the this as acceleration. Then acceleration times t will give you the final velocity in y direction. Okay, so then after that, the angle x, the angle will be tangent inverse of vy over vx. Okay, and that gives you that number over there. Problem 5, we went through that in version A. So this is again on Gauss's law. You'll be using Gauss's law to calculate this one. Okay. Number 6, we also went through in part A. So yeah, so we can skip that one. Number 7, we went through this in the previous version. Okay, so we can skip this one. Number 8, you have combination of capacitors here. So then you'll treat these two as parallel, purely in parallel first, and then combine them first. Okay, to calculate the equivalent resistance first, or equivalent capacitance first. After that, then the energy stored in this combination will be 1/2 CV squared. Okay, C, you take the capacitance, you take the equivalent capacitance. Okay, so then gives you that number. All right. Number 9 and number 10, we just look at in the previous version. So here we are looking for the current going through this guy. Okay, so then it's this number. And then here we have a different time t. Okay, so this is the difference. So then you will have different current. Okay, so this is the two versions, the solutions for the two versions of exam 2. All right. Do you guys have any questions on the two versions? All right, so it looks like we are good. So then, no, not this one. Let's go to our class lecture PowerPoint slides. Okay, so although we are using the online format, but the PowerPoint slides, they will still be on Moodle. Okay, so you can refer to Moodle for the PowerPoint slide. Now you don't have to open it because I will be sharing my screen to you, so then you see my screen over here. Okay, so let's get started on the lecture part here. Let me put into the full screen mode. Okay, so we had 2 classes on the magnetism, so we'll be continuing the magnetism this time. Okay, so briefly, the last time we looked at the Hall effect, which says if you have a conductor, this rectangular shape as a band of conductor, if there's an external magnetic field, in this case, the B is the magnetic field, that is, you see the crosses here, that means it's going away from you. So the magnetic field is pointing towards the, into the paper, okay? And then if that is the case, then the charge carriers inside the conductor will experience magnetic force. You can use your right-hand rule to determine this. So your thumb will be going along the direction of the velocity, so go in that way, and then your forefingers is going to be going in the same direction of the magnetic field. So put your right hand like that, so then the force will be perpendicular to the palm going upward, okay? So that's why the force is going upwards if this is a positive charge. So in that case, then there will be positive charge built on the upper side of this conductor. Then there will be negative charges building up on the negative side here. So then you'll have electric field, okay? So then this charge will carry electric field, or this charge will experience electric force, okay, in the opposite direction of the magnetic force, okay? At a certain point later, these two forces will be imbalanced, so then you'll have no more electric field strength going up, okay? So electric field strength is going to stay at particular value at a certain point, okay? So then you can use the device that called a voltmeter to measure what's the electric field or electric potential build on the two sides of the conductor. And then according to the signs of the voltage, you can tell if it's a positive charge carrier or negative charge carrier, okay? So this is called Hall effect. You can use Hall effect to, one, determine the signs of the charge carriers, and then you can use it also to determine the strength of magnetic field if the magnetic field is unknown. And then in that case, you would already know what's the charge carrier and then the number density of the charge carrier, okay? So that's a Hall effect. And then later on, before we had a break, before we had exam 2, we talk about the magnetic force on a charge, on a current carrying conductor. So if you have wire that carries current inside the magnetic field, now basically the current is due to the movement of charges, okay? So we know that for a moving charge, it will experience magnetic force. So then in this case, for a wire carrying so many charges moving in one direction, so all these charges will experience magnetic force, so that magnetic force on each of the charge will build up, and it's going to be on the wire, okay? So the wire then will experience magnetic force if it's placed inside a magnetic field. The magnitude of the magnetic force on the wire is going to be equal to the current inside the wire I times the length of the wire L, and then times B, the magnetic field strength, okay? Times the sine of angle theta. The angle theta is defined as the angle between the wire, direction of the wire that's having the, that's in the direction of the current, and then the direction of the magnetic field, B, okay? Now, in a vector form, it's going to be the cross product of the two vectors, okay? So we will not talk about it. I think we mentioned that briefly in the class, but that's not important because this is not a calculus-based class, okay? So, so that's when we have a wire carrying current inside a magnetic field. So today we'll be looking at the torque on the current loop, okay? So imagine if you have a current loop or a loop made by wire, and then inside the wire, there's current going through, okay? So you can imagine that if there are two open terminals at somewhere here, so typically, I mean, you don't have a loop wire that carries the current itself, but typically this is what you have, okay? So typically you'll wind the wires through say a rectangle or a cylinder, okay? Then there's so many loops inside it, okay? So you can imagine you're just taking one loop out of it, okay? Now, when a wire is wrapped around a say a rectangle or cylinder, you have two ends of the wires at the end, so you can send the currents through the two ends. Okay, but just imagine we are just taking one loop out of it. Okay. So then if this loop is being placed in an external field, B here in the indicated by this blue arrows here in the figure, so then you can see you can break the loop into 4 wires, the top wire, the bottom wire, the left wire, and then the right wire here, okay? So according to what we just learned in the previous section, then each of these 4 wires might experience magnetic force, okay? So we'll apply then let me share you with the what I have on my note here. So I'm going to, okay, I need to switch my camera. Okay. So let me see. Just make sure you can see this, okay? So each of the wire will experience force according to F equal to ILB sine of theta, okay? So this is the equation we are going to use to determine the magnetic force experienced by each of these wires, okay? So let me put this in full screen mode. All right, so on the top wire here, you can see I has the same direction as B, where that determines the theta, okay? So on the top wire here, then you'll see that the theta is going to be 0, all right? Now, on the bottom wire, you can see B is in this direction to the right. In the bottom wire here, you can imagine the current goes through the side here, will be going towards left on the bottom wire, okay? So I and B will make an angle of 180 degrees, okay? So either the top wire or the bottom wire will have force equal to 0 because sine 0 equals to 0. And then so ILB doesn't matter because sine theta is going to be 0. On the bottom wire here, ILB, you'll be doing ILB, let's see. Okay. On the bottom wire here, okay, that's ILB sine of 180 degree, okay? Now sine of 180 degree is also 0, okay? So then on the top wire and the bottom wire, you got both magnetic force equal to 0, okay? Now we will take a look on the side wires here, on this side and that side, okay? So on the left-hand side, we'll look at on the left-hand side here, okay? So I is in this direction, is going upward, okay? The B is going horizontally. So then the angle theta on the left, okay? So on the left wire, the theta is going to be equal to 90 degree, all right? So then force is equal to ILB sine of 90, which is equal to 1. So force is ILB, okay? On the right wire, up here, on the right, the theta is also going to be 90 degree because the current here goes downward. If you look at the PowerPoint over here, it's going downward. The B field is going to the right. So it's still 90 degree, okay? So then force is going to be ILB, all right? The only difference between the force on the left wire and right wire is they are pointing in the opposite directions, okay? You can use your right-hand rule. So on the left wire, if you look at the PowerPoint over here, because the current is going upward, okay? Now on the right wire, the current is going downward, okay? The B field is in the negative, in the right hand, pointing towards the right-hand side. So B field is the same. Now, if you have current in the opposite direction, then these two wires will experience force in opposite direction. So you can use your right hand rule to determine this, okay? Put your thumb in the direction of the current, to put B field in the direction of your fingers, okay? On the right hand side. So on the left hand side of the wire, on the left wire. So then on the left wire, the magnetic force is going to be pointing towards or into the board, okay? Towards the board, into the board. And then on the right hand side, it's going to be out of board, okay? So with a cross, that means the force on this side is going into the board. On the right wire here, the force is going to be pointing outward with a dot, okay, to represent that direction. So you can see two forces on the loop, okay? One force on the left wire, the other one on the right wire. And then they are pointing in the opposite direction. So imagine two forces pulling left-hand side wire and right-hand side wire. So this loop is going to rotate because of these two forces, okay? It's going to rotate about the exit going through the center in this dashed line, okay? So then you get overall a net torque on the wire, on the loop, okay? On the loop made of the wire. All right. Now, the amount of the torque, okay? So if you don't remember, for the torque, we use this symbol, looks like T, but it's called tau. It's going to be equal to F times the distance, okay? So F is ILB. In here, the length will be the height of the loop, okay? The distance, this will be 1/2 of the width, okay, towards the center axis, okay? So this is the torque by the left hand wire. This is the torque by the right hand wire. They are the same magnitude, okay? So it's going to be equal to I times B times H times W, okay? Because 1/2 W plus 1/2 W will be W. So IBH times W. Now, height times width of the loop will give you area, okay? So H times W equals to area. So then the torque on the loop is going to be equal to the current in the loop times the area of the loop times the magnetic field, okay? So I times A times B, that gives you the torque, all right? Now, although we derive this from a rectangle loop, the torque on a current carrying loop will be also for, it'll be this equation also for other shapes, okay? You can have a square loop, you can have a circular loop, okay? Or you can even have a, say, oval kind of shape or loop or whatever kind of irregular shape. It's going to be I times A times B, okay? So take a note, this torque equals to I times A times B applies to also other different shapes, okay? All right. So now when we look at the loop in the 2 slides ago, we have this loop in the same plane of the magnetic field plane, okay? So let's go back. So this is where the loop, the electric field plane, okay? On the paper here, the loop sits right on this plane, okay? So that's the case. But now in general, if we look from the top here, so if this is the loop, we are having the top view of the loop, so you only see one side of it, okay? You let the loop stand vertically, so then you look from the top, so you will see just one side of it, okay? So this is what we have 2 slides ago when this loop is in the same plane of the B field, okay? Now in general, you might have a loop that is having an angle with your magnetic field, okay? So again, this is the top view of the loop. So the normal direction of the loop and the magnetic field makes the angle of theta equals to any number, okay? It could be 0, could be 90 degrees, could be whatever. In this case, when we had the loop in the same plane, on the same plane of the magnetic field, it's making a normal angle or a 90-degree angle. Okay, so in this case. So then in general, if you have an orientation like this, where there's an angle between the normal direction of the loop plane and the magnetic field direction, so then the torque will be given by this equation, okay? I times A times B times sine of theta, okay? In the case we looked 2 slides ago, theta is equal to 90 degrees, makes a normal angle. So then we don't have that term because sine 90 is equal to 1, okay? So torque is equal to, in general, I times A times B times sine theta. The SI unit for torque is newtons times meter, okay? So it's basically force times distance times the sine angle. So Newton times meters, all right? Now, more often you have so many identical loops, okay, in the arrangement of one by another, then you have the same current going through all these loops, okay? So in normal, or more often, there will be n turns of identical loops of the same area A. So then the overall torque the n terms of identical loop is given by the equation at the bottom of the slide, okay? So torque then is equal to number of turns times I times A times B times sine theta, okay? So this is, if you have more than one loop, okay, you have n identical loops, then that's the equation you want to apply. All right, and again, as I said, the torque, this equation applies to any other loops, okay? Other shapes, okay, of loops. All right. The next one here, next section in this chapter talks about magnetic field produced by currents, okay? So at the beginning of the chapter, we mentioned that any magnetic field actually is produced by either moving charged particles or currents, because currents is basically you have many moving particles confined in a conductor, okay? So then if you have a conductor or wire that carries current, then you can have magnetic field produced by that current carrying wire, okay? So in this case, say if there are 2 wires carries current I1 and I2, so then there will be a magnetic force produced by the 2 wires, all right? So so to determine what would be the magnetic field, we use actually a law called Ampere's law, okay? So that gives you a formula how to determine what would be the magnetic force. So this one is very similar to the Gauss's law we talked in the electric field. When we say we can use Gauss's law to determine electric field, this is similar law here on how to determine a magnetic field, okay? So, but in this case, so if there's a wire, or say a couple of wires that are close to each other, so then this is the direction of the magnetic force, okay? I think we mentioned this in the beginning of this chapter as well. I don't remember either section 4 or 5. So you can use a right-hand rule to determine what's the direction of the magnetic force, okay? If you have wire, then you are going to align your thumb with the direction of the current in the wire. The 4 fingers then curve around will be the direction of the magnetic force, okay? So then if there's a wire, you will have a circular magnetic field around the wire, okay? And then the magnitude of the magnetic current is the proportional, inversely proportional to the distance to the wire, okay? Proportional to the current, but inversely proportional to the distance away from the wire. So then using Ampere's law, this is what you get, okay? So the tangential direction of the magnetic field times the small dl, okay? So if you have in this circular path, then b will be the same. So you'll be doing b times then just the circumference of the circle here, okay? So it'll be b times 2 pi r will give you mu naught times I enclosed by this closed path, okay? So similar to like the q enclosed divided by epsilon naught, but in this case you have mu naught multiplied by that, okay, by the current enclosed. This mu naught is a constant number, is equal to 4 pi times 10 to the negative 7 Tesla times meters times ampere, okay? So and then this is called the permittivity of free space, okay? Now this applies to the free space. Now in other material, mu will be a different number, okay? So this is basically what Ampere's law says, okay? It says sum of the B parallel, which means tangential times delta L over all segments of a closed path is equal to a constant mu naught times the current enclosed by the path, okay? All right, so then if you have a wire, just a wire carrying current I, okay, at distance R away, okay, so then you can do this. You can do B times the circumference 2 pi r is going to be equal to mu naught times I. So then this is the magnetic field, okay? So B then is equal to mu naught I divided by 2 pi r, okay? And this is called right-hand rule 2. So right-hand rule 2 says you align your thumb in the direction of the current, the four fingers curled in the directions of the magnetic field, okay? All right. So let's take a look at the examples here, okay? So this one says find the magnetic field 7.25 centimeters from a long straight wire that carries a current of 6.81 amp. Okay, so for this one, it's going to be straightforward. We are just going to apply the equation we had in the previous slide, okay? So you are going to use the equation B is equal to mu naught I over 2 pi r, all right? Mu naught is 4 pi times 10 to the minus 7 Tesla meters over amps, okay? Times the current of 6.81 amps divided by 2 pi times 7.25. It's in centimeters, so you convert it into meters, okay? So then at the end, this is going to be, I calculated earlier, it's going to be 1.88 Tesla. Okay, so that's the strength of the magnetic field. All right. So anytime if you have questions, just unmute yourself and then you can just go ahead and talk, okay? So any questions you guys might have? All right. So if not, then we're going to look at the second problem here, or second example here. All right. So the second example here is a little bit more complicated, okay? So we have these two long wires. Now, these two wires, they are perpendicular to the paper or to the screen here. One wire carries the current going into the screen, okay? So into the screen, that means you see an arrow, the backside of the arrow that going away from you, so going into the screen here. The other wire on the right here carries the current that goes out of the paper or the screen towards you, so then you see a dot, okay? So imagine these are two wires perpendicular to the screen, okay, carries two current. Now it's asking you what would be the magnitude and direction of the magnetic field, net magnetic field at point P. Okay, so by one single wire, you will have one magnetic field. Okay, and then by a second one, you'll have a second magnetic field. Okay, so let's take a look on this one here. So you have this wire carries I1, and then you have this wire carries I2. All right, and then this is a square arrangement over here on this square here dash. 5 centimeters for the sides, for each of the sides here, 5 here and 5 here. You're looking for B field at this particular point P. Okay. Now, by a single wire, the magnetic field is going to be around the wire. It's going to be a circular path. Okay, so over here, it's going to be by one. It's going to be something in this big circle here. Okay, now you can use your right hand rule. So your thumb is going in the same direction as the current. This current going into the ball. So you're going to put your thumb in this way, and that way going into the ball. Okay, you curl your 4 fingers in this way. So then current or magnetic field at this point by I1 is going to be in this direction. Okay, this will be B1. All right, magnetic field is a vector. All right, now magnetic field by the second current carrying wire I2 here will be you are going to use your right hand rule again, the second right hand rule. So the thumb is in the direction of the current, so going out of the paper, out the ball. Okay, then you curve your 4 fingers. So then at particular point P, it's going to be in the tangent direction of that point P. So it's going to be in this direction, perpendicular to this diagonal line, but in that direction. This will be B2. All right. So you have B1 by I1, you have B2 by I2. So then your overall B is going to be equal to B1 plus B2, okay, in vector form. All right. So I know you guys still probably don't like vectors, but that's what we have to deal with, okay, unfortunately. So this is the X and Y coordinate system, all right. Now you can see B1 is along the horizontal direction. So that means B1 will be purely just in X direction, all right. The magnetic field that is not so nice is B2, because B2 is having a particular angle here, all right. So 90 degree to the diagonal line, that means 45 degree over here, all right, and then 90 degree here. So 45 plus 90. So for B1, all right, it's going to just have the magnitude B1, and then the angle will be 0 because it's in the horizontal direction. For B2, it's going to have a magnitude B2, but the angle is going to be equal to 135 degree, okay? The 45 degree plus the 90 degree, and then below the x-axis, so that means negative, okay? Negative 135 degree, all right? For B1, for the magnitude, it's going to be determined by the equation a couple slides ago, B equal to mu naught I over 2 pi R, okay? Because we are looking for B1, then you use I1 and R1. All right, I1 is given as 3, so I1 is equal to 3 amps. That's given. R1 will be the distance of your point of interest to the wire, so it will be the side of the wire. So R1 will be 5 centimeter, okay? So you can plug the numbers into the equation, you can determine your B1, the magnitude of it. For B2, the magnitude of it, you can also use the same equation, but you use I2 and then R2. Okay, I2 is given as 4 amps. R2 will be the distance from your point of interest to your wire. So this will be the diagonal, the length of the diagonal here for the square. So for the diagonal, then it's square root 2 times 5, okay, centimeter. So square root 2 times 5 centimeter. That will be R2. You can also plug in the numbers. You can have the magnitude for B2, all right? Okay, so then, but we are looking for B1 plus B2 in vector form, all right? So then we'll be doing the vector addition. Again, you guys don't like it so much, but we'll deal with it, okay? So B is equal to B1 plus B2. Then that means we are going to look at the x component of B, which will be equal to the x component of 1 plus the x component of the 2, the second one, okay? Not so bad. For the y component of the B, then it's going to be y component of 1 plus y component of the 2, all right? Now, for B1x, x component of B1 will be just B1, okay? So let me see. We can have B1 calculated, all right? So B1 is going to be 4 pi the mu naught times I1 times I1 3, okay, divided by 2 pi times 5.0 times 10 to the negative 2. All right. So you can see 4 pi, we will cancel out 4 pi out of the, 2 pi will cancel out 2 pi. So we have 2 remains over here. So it'll be 6 over 5. All right, 6 over 5 is 1.2 times 10 to the second Tesla. Okay, that's B1. Similarly for B2, it's going to be 4 pi times I2 divided by 2 pi, okay, square root 2 of 5 times 5 times 10 to the negative 2, all right? So again, 2 pi will cancel out 4 pi, so it's 2 remains, all right? Now square root 2 will cancel out 2, so then you have square root 2 remaining on the top, all right? So this will be 4 over 5 gives you 0.8 times square root of 2, okay, times 10 to the second Tesla, all right? So that's that one. You can further calculate 0.8 times square root 2, okay? It would be something like 11 point something, close to 12, okay? But I'll just leave it by like that, okay? So with that, we can calculate bx and by, because b1x then will be just 1.2 times 10 to the second, okay? b1y will be 0 because b1 doesn't have y component, it only has x component. I'm going out of the paper, okay? So b1 only has x component, its y component is going to be 0, right? b2x then is going to be equal to b2 cosine theta 2, all right? So it will be the 0.8 square root 2 times 10 to the second, okay? All this together, cosine of negative 135 degrees, okay? So we can calculate that. This will be 0.8 square root 2 times 100 times cosine of 135 degree. That will be, for cosine, it's going to be negative 1 over square root 2, okay? Yeah, I know it, but you guys can calculate, use your calculator, okay? It doesn't really matter. So this is going to be square root 2 and square root 2 will cancel out, okay? So it's going to be minus 80 remaining Tesla, okay? That's the x component. Now the y component will be b2 sine theta 2, okay? So it'll be again 0.8 square root 2 times 100 sine of negative 135, okay? So this one again will be negative 1 over square root 2, okay? Sine of 1 negative that. So square root 2 and the square root 2 will cancel out. Again, will be negative 80 Tesla, okay? For the y component of this guy. So then now go back to the bx. It's going to be b1x will be the 112, okay? So 112, oops, 112 minus 80, or plus minus 80, okay? That's b2x. That gives you 40 Tesla, all right? by will be, b1y will be 0 plus, okay? b2y will be negative 80. Okay, that gives you negative 80 Tesla, all right? So then your overall B will be equal to 40 Tesla in the X component minus 80 Tesla in the Y component, okay? Now I think somewhere I'm missing the 10 to the minus 7. So yeah, for the mu naught, it's 4 pi times 10 to the minus 7, okay? So sorry about that, but this one should be multiplied by 10 to the minus 7. So all this number will be multiplied by minus 7, 10 to the minus 7, 10 to the minus 7, okay? So, well, we can correct that later, but all this should be minus time multiply 10 to the minus 7, okay? So you can leave it like that, okay? That will be the X component and Y component, okay? And then if you want, you can calculate what's the magnitude, okay? So the magnitude will be square root of the X component square plus the Y component square, okay? And then times 10 to the minus 7, okay? That will be equal to, at the end, it's going to be 8.9 times 10 to the minus 6 Tesla, okay? So that will be the magnitude. Then the angle, direction angle will be, you do tangent inverse of y over x, okay? Keep in mind the x is minus or x is positive, so it doesn't matter, okay? So then you'll get minus 63 degrees, okay? That's the angle, all right? Sorry, messed up in the middle, but got it fixed at the end, okay? So it's a little bit complicated on this one because the factor that we are dealing with the vector addition, okay? All right, so any questions you guys might have? All right, so let me see. If not, then I think we are going to stop over here for today, all right? So yeah, and then I'll probably make this available online at some point later, so you can again come back to the video, and if you didn't get at some point you didn't get it, you can just review it, okay? Or let me know if you have any questions. I think earlier last week I sent out the link, email link, that you guys can reach me on one by one. So click on that link. I think I sent out email title as office hour. Okay, so you can click on that one. Then you can talk to me about. We can do the Zoom meeting for the office hour by that way. Okay. All right. So that'll be it for today. On the lab, we'll start lab next week, but let me just give you briefly about the lab. So what we are going to do from this point on is we are going to look at like some of the demos, and then from that point on, I will give you guys some data that I had from the previous groups, so you can work on the data and then write your lab reports. Okay, so that's what we are going to do for the labs from next week. So from next week we'll have lab. Okay, but I will send you out another link for the lab. We'll be meeting again on Zoom, starting with the demonstrations, and then I'll give a briefly summary of what you would be doing if we would actually have a lab, okay? And then after that point, you guys will receive some data, you'll work on the data analysis, and then writing the data reports, okay? All right, so Any questions you guys might have? Just unmute yourself and then say something. Otherwise, we'll stop here and then see you guys back on Monday. Okay, everyone have a good weekend. Be safe. Stay healthy. Bye.